Hey everyone, welcome to this explainer. Today, we're taking a pretty incredible journey, going straight from abstract physics to the actual physical tools that keep the whole industrial world running smoothly. If you're studying instrumentation, or, if you've ever just wondered how massive power plants keep their complex systems from literally blowing their tops, you are absolutely in the right place. We're going to break down the fundamentals of industrial pressure measurement. We'll get into what pressure actually is, the different ways we categorize it, the surprisingly diverse language of units we use to measure it, and finally, those ingenious mechanical elements that translate an entirely invisible force into something we can actually read on a dial.
Okay, let's dive into this. Here's our theory to application blueprint. 1. The physics of pressure. 2. Types of pressure. 3. Units and conversions. 4. Mechanical sensing elements. And 5. Manometers and calibration.
So Section 1, the physics of pressure. Before we measure anything, we've got to understand what this invisible force actually is. To ground all this math in reality, let's think about something you've probably done 100 times. Why does a sharp knife slice right through a piece of fruit effortlessly, but if we flip that exact same knife over and try to cut with the flat spine of the blade, it doesn't do anything but just kind of bruise the fruit? We're applying the exact same amount of effort, right? So what actually changes? Well, the answer lies right here in this equation. Pressure equals force divided by area. In physics, pressure is defined as the physical force exerted perpendicularly on the surface of an object per unit area. Going back to our knife, when we press the flat spine against that fruit, our force is spread out over a relatively large area, which means we get low pressure. But when we turn the blade, so that razor-sharp edge is what's touching the fruit, we apply that exact same force over a microscopic surface area. The pressure just vastly increases, and it cuts easily. Same force, entirely different pressure. Now, in the scientific community, the language we use to measure this force is the Pascal, which is the standard SI unit of pressure. To actually visualize a Pascal, just imagine a force of exactly 1 Newton distributed evenly over a surface area of 1 square meter. So it's a very precise, defined metric, literally 1 Newton per square meter. And this brilliantly illustrates how this builds into an exact relationship. Imagine a block with a weight or force of 100 newtons resting on an area of 0.1 square meters. Doing the math, that generates 1,000 pascals of pressure. Now, take that exact same block and stand it up on its narrow end, which has an area of just 0.001 square meters. We haven't added a single ounce of weight, but the pressure absolutely skyrockets to 10,000 pascals. Understanding this inversely proportional relationship between area and pressure, that is the absolute foundation of all industrial instrumentation. Moving right along to Section 2, Types of Pressure. Let's see how this invisible force actually interacts with our environment. Now, what's really interesting here is thinking about how, right now, you and I are basically sitting at the bottom of a giant ocean of air. Atmospheric pressure is simply the pressure caused by the weight of the atmosphere sitting right above us. Down here at sea level, this is roughly 14.7 pounds per square inch, or PSI. It's acting constantly on literally everything. We don't really feel it, because we're entirely used to it, but in industrial measurements, we absolutely have to account for it. And that brings us to the practical difference between gauge pressure and absolute pressure. The clearest reference point is zero pressure, which really only exists in a total vacuum, like deep space. Pressure measured from this absolute zero point is called absolute pressure. But let's be real, out in a chemical plant or a power station, most industrial gauges do not care about the total vacuum of space. They're calibrated to read zero at our normal atmospheric pressure. They're only measuring the difference between the actual process pressure and the atmosphere around it. We call that gauge pressure. So mathematically, absolute pressure just equals gauge pressure plus atmospheric pressure. Oh, and it's also worth noting we sometimes measure differential pressure, which is just the direct difference between two separate measurement points. That one's highly useful for measuring things like flow and liquid levels.
All right, Section 3, Units and Conversions. Because different industries use totally different metric and imperial languages to quantify all this. Since instrumentation is a truly global field, we use a surprisingly diverse vocabulary of units. In the US, you are going to see a lot of PSI, pounds per square inch. 1 PSI equals roughly 6.895 kilopascals. We also frequently encounter the bar, which is a metric unit defined as exactly 100,000 pascals, or kilogram force per square centimeter, and the att, which just stands for 1 standard atmosphere. You'll even see physical fluid heights used as units, like inches of water, and the torr, which is super common when you're dealing with vacuum measurements. So the crucial point here is really grasping the sheer scale of these units. One standard atmosphere, that baseline pressure we live in every single day, is equal to a massive 101,325 pascals. That number just goes to show you that a single pascal is an incredibly tiny amount of pressure. And because it's so small, in practical industrial applications, you're almost always going to see it scaled up to kilopascals, or kPa, just to keep the numbers manageable on our instrument screens.
Which brings us to Section 4, Mechanical Sensing Elements. How do we actually translate this invisible force into readable mechanical movement? Well, industry relies heavily on Bourdon tubes. These are curved metal tubes that literally try to straighten themselves out as pressure increases inside them. A standard C-type tube, which is bent at 270 degrees, handles lower ranges up to 60 bar. But spiral or helical tubes, they have way more windings, so they can handle massive ranges, literally up to 7,000 bar. Then we have bellows. Think of these as expanding, accordion-like metallic containers made of materials like phosphor bronze or stainless steel. And finally, we have diaphragms, which are thin, flexible circular membranes, and capsules, which are essentially just two diaphragms welded together.
Let's move to and see how this builds, right? Like, why would a facility choose one over the other? Well, bellows are fantastic because their expanding container design allows for a large degree of physical movement. But what if we're measuring something incredibly subtle, like the draft pressure in an HVAC system? That is exactly where we use a capsule. By welding two corrugated diaphragms together, a capsule literally doubles the physical displacement compared to just a single membrane. This makes capsules incredibly sensitive, making them absolutely perfect for highly precise, low-pressure applications, typically ranging from 0 to 1,000 millibar. And finally, Section by manometers and calibration. This is one of the most accurate, fundamental ways to measure low pressure.
Manometers rely on a beautifully simple hydrostatic equation. Pressure equals the fluid's density times gravity times the height of the fluid column. We literally balance process pressure against the actual physical weight of a liquid. We can do this using a basic U-tube, a well type for easier single-column reading, or an incline manometer for maximum sensitivity at low pressures. And the fluid you choose changes everything. Water has a density of 1,000 kilograms per cubic meter. Mercury, on the other hand, is over 13 times denser. So if we need to measure a much higher pressure without building a glass tube that goes straight through the roof of our lab, we just use a heavier fluid like mercury. It requires a much shorter column to balance the exact same amount of pressure. Pretty clever, right?
We've really gone from the invisible mathematics of force and area right down to the heavy liquid of a manometer. As you walk out into the world today, or step onto the floor of a manufacturing plant, try looking around with this new perspective. Consider the Bourdon tubes silently uncoiling in the pipes around you, and the actual atmospheric weight resting on your shoulders. What invisible pressures are acting on you and the mechanical systems around you right at this very moment? Thank you so much for exploring this topic with us today, and keep learning.